Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In the last lecture, we discussed electronic spectroscopy of many electronic atoms. We also carried our discussion towards the types of systems where not only I have more than one electrons, I also have more than one nucleus. So, therefore, we are in the realm of molecular spectroscopy, but we are still keeping our discussion simple, and we are talking about the electronic spectroscopy of diatomic system. We discussed that for diatomic system and therefore, can be extended to polyatomic systems, we can construct the molecular orbitals as linear combination of atomic orbitals, because a molecule is composed of several atoms. Each atom brings its electrons, but once the molecule is formed, the electrons belong to the entire molecule. So, now by constructing this linear combination of atomic orbitals, of course, we discussed also as to what are the conditions of which the linear combination should follow. For example, the combining orbitals should have similar energy, they should have a good overlap. So, keeping all these things in mind, we can construct molecular orbitals. For diatomic system, whether homonuclear or heteronuclear diatomics, the molecular orbitals are easily constructed. For polyatomic systems as well, you can for smaller system you can construct them by hand, or as you go larger and larger systems, you can construct the molecular orbitals by doing electronic structure calculation by the help of some computers. So, computationally, even for large molecules, we can construct the molecular orbitals. Once we have the molecular orbitals, then we follow something Aufbau principle and fill electrons depending on how many electrons we have in that molecule, starting from low lying orbitals going upwards. We also make sure that only 2 electrons are being given to one molecular orbital, and depending on the electronic configuration, as we have seen in case of many electronic atoms, every electronic configuration gives rise to different electronic states. So, based on depending on the configuration that we have created, we can also have the electronic states. Comparing the situation of many electronic atoms and molecule, one similarity is that of course, both of the systems have many electrons. The difference starts from the fact that in a molecule, the electrons experience more than one nucleus. So, the nuclear field in case of a molecule is extended. So, the electrons are subjected to greater electrostatic field arising from the nuclear framework. So, that we have to keep in mind. Otherwise, as long as you have a molecule, you have a set of electrons. So, the electrons are once the molecule forms, the electrons belong to the molecule, and therefore, the analogy that we had, or the information that we obtained while considering many electronic atoms, that each electron will have its orbital angular momentum and spin, but when in a many electronic system or in a molecule, when you have more than one electrons, we can also have a total angular momentum and a total spin. So, in today's class, we will do this discussion as to classification of electronic states for diatomic molecules. So, the point that we have here is that the total angular momentum of the system can be obtained by the sum of the individual angular momentum of the electrons, and similarly the total spin of the molecule can also be generated by combining the spin of individual electrons in that molecule. The way we did for many electronic atoms is somewhat similar, but then we will also discuss about what are the essential differences. So, we have this L and S. When we are discussing about many electronic atoms, we also said that we can characterize the states by the so called LS or Russell-Sanders coupling scheme or JJ coupling scheme. We said that when the coupling between the electronic orbital angular momentum and the same electron spin is weaker or moderately strong, we can safely use LS coupling scheme. But when the spin orbit coupling between spin and the orbital angular momentum of an electron are heavily coupled, in that case neither L nor S remains a good quantum number. So, therefore, L plus S or the J or the total angular momentum becomes the good quantum number. So, therefore, an electron is identified with its J quantum number in a situation where there is strong spin orbit coupling, and in those cases, for example, in case of very heavy atoms, we use the JJ coupling, because the coupling between two electrons of an atom are determined by their J quantum numbers, not L or S, because they are no longer good quantum numbers for those electrons. But for majority of the atoms, LS coupling scheme is good enough. We will also do the same analogy here. We will consider that for those cases where the spin orbit coupling is either weak or even moderately strong, we will follow LS coupling scheme even for the diatomic molecules, and analogy goes also for polyatomic molecules. So, our discussion is going to be restricted to the LS coupling scheme. Now, one important point is that we will now discuss about each of these angular momentum. Let us first consider this L angular momentum, which is also given as a vector operator. Now, in case of an atom, the electron precedes the nucleus with a fixed orbital angular momentum. So, therefore, the orbital angular momentum L is a conserved quantity for an atom. Therefore, in other words, L can be precisely determined, the orbital angular momentum of an electron in an atom can be precisely determined. But in case of a molecule, what happens is that since there are so many nuclei, the electrons start precessing the nuclear environment so fast that its magnitude is no longer a well defined quantity. So, what does one do then? So, in here what you see in this picture, suppose you have a diatomic system, call it AB or A2, it does not matter, just to be more general we call it AB. So, now an electron is there whose orbital angular momentum is given by this arrow here. This orbital angular the L value, now the electron precesses the nuclear environment so rapidly that its magnitude is no longer a defined quantity. While its magnitude is no longer a defined quantity, the projection of this vector L angular momentum to the internuclear axis, this projection is given by lambda h bar. So, magnitude of L is not defined. In a molecule, but what is defined is its projection or its component of this L vector along the internuclear axis, and this is given as lambda h bar, where lambda is a well defined quantity in case of diatomic molecules. This lambda goes from 0, 1, 2 and so on and so forth. Different values of lambda indicate that the electron is orbiting the nucleus in a different with a different orbital angular momentum. So, these are lambda goes from 0, 1, 2 and so on and so forth. For all non-zero value of lambdas, so when lambda is 1 or 2 or 3, these states are degenerate. Why? Because you can see you can have lambda as 1 where the electron is orbiting in clockwise, or lambda is 1 when the electron is orbiting anti-clockwise. So, therefore, to account for clockwise or anti-clockwise orbiting of the electron, we have the degeneracy. Of course, this is a classical description of the picture, just to give a physical understanding to why this lambda 1, 2 or non-zero value of lambda are degenerate. You can keep this in mind, but I should remind you that this is a very classical way of describing. When we come to lambda equals 0, Of course, there is no orbital angular momentum, that means there is no orbital motion of this electron. So, therefore, lambda equals 0. When it is lambda equals 0, there is no question of having a clockwise or anti-clockwise precession. So, therefore, this is non-degenerate. Now, if you remember, when we had L equals 0, in case of atoms L equals 0, 1, 2, 3, so on, we called them as capital S, P, D, F and so on. Similarly, when in case of diatomic molecules, when lambda is 0 or 1 or 2 or 3, we call them Sp, but then we use the Greek symbol sigma, pi, delta, phi and so on and so forth. So, for diatomic molecules, we would use sigma pi to define the electronic states. If you remember, we used S, P, D, F, singlet S, triplet P, singlet D, like this for the atomic electronic states. So, this is about the L. Now, let us consider about S, the spin of the electron. The orbital motion of the electron or the orbital angular momentum of the electron is strongly coupled to the internuclear axis or the nuclear field. The electrostatic field that is coming from the nuclei greatly influences the orbital angular momentum. So, therefore, orbital angular momentum L is no longer a conserved quantity for diatomic systems. But spin on the other hand does not couple with the electrostatic environment of the nuclei, but instead it gets coupled to the nuclei, but in a different manner. What happens is that when the electron makes an orbital orbital motion, so it because of its orbital angular momentum, it generates a magnetic field. Of course, the electron's orbital motion is caused by the nucleus. So, now the nucleus is the interaction in the field of nucleus, the orbital angular motion of the electron creates a magnetic field, and this magnetic field interacts with the spin of the electron. So, therefore, the spin also is linked to the nuclear environment. So, this is what is done. So, this vector here defines the spin of the electron. So, the spin, since it does not directly couple with the nuclear environment, so spin still remains a conserved quantity or a good quantum number. Yeah. Then, but what we are looking at is the projection of spin to the internuclear axis. So, which is given as this sigma h bar, where sigma value goes from minus s to plus s in the step of 1. So, therefore, so suppose we have spin equals 0, s equals 0, which is a singlet state, 2s equal, so therefore 2s plus 1 is 1 and this is a singlet state. We have only one value of sigma, and that is 0, from minus 0 to plus 0, and that is 0. If I say s equals half, then 2s plus 1 is 2, that is a doublet state. So, sigma goes from minus half to plus half. S equals 1, that is triplet state, sigma goes from minus 1, 0, plus 1. So, these are the ways that we can define the spin state. So, this of course, this is a triplet state with 3 components, this is a doublet state with 2 components, this is a singlet state with 1 component, and we can carry on. So, now we let us write down what we obtain here. So, suppose we have considered this pi. So, if lambda is 1, so we call that as a pi state, and if the total spin of the system is 3, we would call that as a triplet pi. In case of atom, it would have been some similar nomenclature would have been triplet p, but in case of diatom, it is triplet pi. We have to keep in mind the difference between L and lambda. Lambda is the projection of L onto the internuclear axis. So, this is about the identity of the state in a diatomic molecule. But now what we see that we have this we have this orbital angular momentum and the spin. So, L vector and S vector. So, of course, the limit where there is no spin orbit coupling whatsoever, in that case that is a different matter, but even if there is a weak coupling between L and S, we can define the total angular momentum. Consider this total angular momentum. So, let us now let us consider the total angular momentum. So, now I have L vector here, S vector here. So, I can construct L plus S, and then I get this new vector J, which is given as the way we did for atomic case, and then of course, this the precision of this J vector can also be defined, and the projection of this J vector is onto the internuclear axis is given by this omega h bar. So, the projection of J vector onto internuclear axis gives omega h bar. So, therefore, omega is defined as lambda plus sigma mod value, where lambda is here, sigma is given here, and omega is which is the projection of the total angular momentum onto the internuclear axis. When we have such a situation, consider let us consider one example, that is triplet pi. So, in this case triplet pi, L is 1, that is why we have pi state, S is 1, that is why we have triplet pi, and therefore, what are the possible values of sigma? For to get sigma, we must get lambda, and so we have lambda here as 1, and this is sigma goes as from -1, 0, 1, because this is a triplet state. So, therefore, omega, which is lambda plus sigma, 1 minus 1 is 0, 1 0 is 1, and lambda plus sigma is 2. So, these are the 3 possible values of omega for triplet pi. So, I would write this triplet pi 0, triplet pi 1, triplet pi 2, and this comes when I have spin and orbit coupling or spin orbit coupling. The case that we have defined in this picture goes by this name called Hund's case A. See, the situation that we have is that now we have electron which has orbital angular momentum, electron which has spin. Now, in a molecule, this electron which has orbital angular momentum and spin are subjected to the electrostatic field of the nucleus. So, the nuclear rotation also creates another angular momentum. So, therefore, now there are so many different sources of angular momentum. The different systems would have different kind of coupling. For example, in some molecules may show strong spin orbit coupling, but lower weaker electrostatic influence of the nucleus onto the electron orbital angular momentum. In some other cases, the coupling between the orbital angular momentum and the electrostatic field of the nuclei could be very strong, while spin orbit coupling is very weak. So, therefore, there can be many different possibilities. Considering all different possibilities, Hund outlined 4 different cases. They are called Hund's case A, B, C, and D, which describes different conditions, but Hund's case A is most prevalent, which says that the orbital angular momentum is strongly coupled to the electrostatic environment of the nucleus. The orbital angular momentum and spin are weakly coupled to each other, and the spin of the electron is weakly coupled to the spin of the electron is coupled to the magnetic field being created by the orbital motion of the electron. When these cases conditions are satisfied, this gives rise to the Hund's case A. Similarly, you have Hund's case B, C, and D. So, we will restrict ourselves to Hund's case A and the definition that we have discussed now. Now, coming back to these 3 states that we have, triplet pi 0, triplet pi 1, and triplet pi 2, these states arise when there is L and S coupling, and therefore, we are now entering to the realm of spin-orbit coupling. So, when we have such a situation, we consider now spin-orbit coupling. The spin-orbit coupling induces a change in the energy level of these states, and this delta E, the change because of the spin-orbit coupling, is given by this phenomenological expression that goes as A lambda sigma, where A is a constant, A is the spin-orbit constant, lambda is the projection of L onto the internuclear axis, sigma is the projection of S into the internuclear axis. Now, this spin-orbit constant, the value of this spin-orbit constant keeps changing from one electronic state to another electronic state, but we can obtain it either through computational strategy or even through spectra. We would see how we can learn more about this. Now, this is the energy correction because of spin-orbit coupling. Let us consider now this triplet pi case. In this case, we have lambda as 1, whereas spin is 1. So, therefore, sigma goes as either it can be -1, 0 or +1. So, and we can write omega, which is lambda plus sigma, this is 0, 1 and 2. So, therefore, the state is triplet pi 0, triplet pi 1, triplet pi 2. Now, what will be the delta E for such case? Delta E, we see that assuming this spin-orbit coupling constant is a constant, we call it A. So, what would be the energy for this triplet pi 0? We see that the energy correction would be A, which is a constant, lambda sigma. Lambda sigma is -1. So, therefore, delta E is going to be -A, triplet pi 0. Now, what about triplet pi 1? We see lambda and sigma, if I multiply, then I get 0. So, therefore, delta E is 0. What about the last configuration? We have 1 1. So, therefore, lambda delta E is going to be +A. So, now the triplet pi 0, triplet pi 1 and triplet pi 2 have different energy. Of course, if their energy before the spin-orbit coupling constant is known, consider that E is 0. So, therefore, the energy of triplet pi 0 is E 0 minus A, triplet pi 1 is E 0 and triplet pi 2 is A. So, this is how it splits. So, this is my triplet pi. Because of spin-orbit coupling, I have triplet pi 0, triplet pi 1, triplet pi 2, and what is the n? So, this becomes A. So, this is spin-orbit splitting, a spin-orbit constant in this case. So, energy of triplet pi 0 is lower, but this is true. You see, the value of A spin-orbit coupling constant can be greater than 0 or can be either can be greater than 0 or can be less than 0. When it is greater than 0, of course, the condition that we situation that we described here makes sense, because in this case lowest omega value is low lying. When A is negative, in that case what happens? We get the inverted situation. So, in this case triplet pi when A is negative, and this is the case situation when A is positive. So, based on the value of the spin-orbit coupling, we can have the splitting in this situation. So, now we learn how we can identify the state. We talked about its spin multiplicity, we talked about its orbital angular character, we also talked about its total angular momentum character like triplet pi 2 or triplet pi 1 or triplet pi 0. Now, when we are so far what has happened is that we consider that electron, when it moves around in a molecule, it interacts with the nuclear field, but we have not included any information about the arrangement of the nuclear field in the molecule and its influence. So, now for example, if I am considering a nuclear diatomic or heteronuclear diatomic, or when I go to a polyatomic molecule, I know the nuclear environment changes. Right. In case of homonuclear diatomic, the nuclear environment is symmetric. In case of heteronuclear, it is not. In case of a tetrahedral molecule, the nuclear field has a different shape. It is no longer a straight line like a diatomic molecule. So, the change in the nuclear field is also going to play a role in the electronic electronic states character. So, to incorporate this, now we include in our discussion the molecular symmetry part. So, we have now triplet pi 0, triplet pi 1 or triplet sigma, so on and so forth. So, now consider that we will consider a few cases, since we have our discussion is primarily to diatomic molecules. I will introduce two molecular symmetry related issues here. Suppose I have a homonuclear diatomic A type as opposed to a heteronuclear diatomic AB type. Now, I immediately say that if this is the center of the mass, this molecule A2 has a center of inversion. That means, if I start from this atom, go through the origin and continue to go forward, I will see that I reach the other side and the new molecule would not, I would not distinguish the molecule, whereas this molecule AB does not have center of inversion. So, therefore, the state functions, the electronic functions that will come out of A2 are going to have different symmetry compared to the electronic functions that are going to come out for AB. For example, when the molecule has a center of inversion, the states have definite Gerade and ungerade symmetry. So, G stands for gerade or even, and U stands for ungerade or odd symmetry. So, if it is symmetric with respect to inversion, then it is gerade. If it is antisymmetric with respect to inversion operation, then it is ungerade. So, we normally you must have come across pi G, pi U or sigma G, sigma U type of molecular orbital on this argument. So, therefore, when we are generating the states, so triplet pi 2 or triplet pi state we have here. So, the triplet pi can be triplet pi G or it can be triplet pi U, or you can have triplet sigma G, triplet sigma U or singlet delta G, so on and so forth. So, this G and U represent whether they are even or odd or symmetric or antisymmetric with respect to the center of inversion. Of course, this is applicable only for homonuclear diatomic. For heteronuclear diatomic, since there is no center of inversion, so therefore, there is no question of G or U symmetry. You simply write it singlet delta or triplet pi or triplet sigma, so on. So, there is no question of G or U symmetry. That apart, whether it is homonuclear or heteronuclear, the diatomic molecule is along an axis. So, therefore, there comes another symmetry element, that is reflection across sigma v, where sigma v is any plane containing this diatomic molecule. So, if the reflection across any sigma v is symmetric, then we call this, we give note this with a plus sign, and when it is antisymmetric or it is not symmetric, in that case we give it as minus sign. So, this is mostly important for the sigma levels. So, you must this is, so this tells that this is a sigma state with ungerade symmetry with symmetry with respect to the reflection across any sigma v, which contains the nuclear axis. And in this case, this is negative, suggesting that it is antisymmetric with respect to that symmetry operation. Of course, we do not normally say this plus or minus sign for triplet pi or triplet deltas, because you remember this triplet pi or triplet delta or all pi or delta or phi states, they are doubly degenerate. One of these component is symmetric with respect to the reflection, the other component is antisymmetric. So, therefore, it goes without saying that one of them is the plus, another is minus, and we do not normally write triplet pi plus minus, triplet but this becomes very important for the sigma case. Now, we will just summarize the electronic spectroscopic part and talk about the selection rules in electronic spectroscopy of diatomic molecules. So, again, to obtain the selection rule, we must consider the symmetry of the electric dipole transition moment integral. So, which says some of the selection rules say that G to U, if in case only when this is applicable only when the molecule has center of inversion, G to U is allowed, but G to G or Gerade to Gerade or Ungerade to Ungerade is not allowed. This selection rule arises because the electric dipole moment operator itself is Ungerade symmetry. So, therefore, it can only couple two states with opposite opposite symmetry in G or U sense. Sigma plus to sigma minus or sigma minus to sigma minus, but not mixed case sigma plus to sigma minus. Why so? That is because again the electric dipole moment, the dipole moment in a diatomic molecule is along the nuclear axis. So, therefore, it is symmetric with respect to sigma v. So, since the operator is symmetric, so therefore, both side has to be either sigma minus or sigma plus sigma plus. The change in lambda is either 0 or plus minus 1. Please remember, this is slightly different from delta L in what we saw in case of atoms. The difference being in case of molecules or diatomic molecules, lambda is now the projection of L onto the internuclear axis. So, the selection rule is different. Given that delta S equals 0, that is spin selection rule, only singlet to singlet, only triplet to triplet, that is of course valid only when there is weak spin orbit coupling. Together with delta S and delta lambdas, we can also obtain this delta sigma as selection rule, which goes as 0 to plus minus 1. Delta sigma is the projection of the J vector, where so the J quantum number delta J should be 0 or plus minus 1, but there are some specific rule as to 0 to 0 transitions are not allowed. J 0 to J 0 transition are not allowed. So, these are the selection rules. Each of these selection rule is obtained by considering the symmetry elements of the system in hand, and we can also extend this selections rule to any other molecule of our choice if we know its symmetric properties. So, we would stop our discussion here. Just to refresh your memory, we discussed about how we can classify the electronic states in a diatomic molecule and what are the selection rules for spectroscopic transition in the electronic spectroscopy of diatomic molecules. In the next class, we will continue our discussion on this topic. Thank you for your attention.